He is an associate at Arup Partners, where he's worked since 2000, first in London, now in Madrid. And since 2002, he's also been an instructor, a structural tutor at the prestigious design lab AA in London, and now at the School of Architecture, i.e. Business School in Madrid. He studied civil engineering at BTU Koppitz in his native Germany, after spending much of his youth living in the US and taking advantage of both sides of the Atlantic. And here, without further ado, is Jan-Peter Koppitz.
Thank you very much. Thank you very much. Hello, everybody. Thanks for coming to my presentation, which is not only an adventure in engineering, but actually my adventure in engineering. I worked on the project for the 6 years that I was in Madrid. Now that the project is finished, I've moved offices, actually, update on my biography, and I now work in San Francisco. So now I'm over here in North America. But yeah, now I want to talk about my adventure in engineering, 6 years that I worked on a small timber project. For those of you who haven't seen it, let's just go through these, these slides. I think you've seen them often enough. And here we are. Here are the timber mushrooms, as the locals in Sevilla call this project, which is really good. Once the locals, give a nickname to your project, then you know, okay, they've accepted it, and now they really like it. So they call them las setas. And here are the timber mushrooms on opening day in March 2011. As I mentioned, for me, it was 6 years working on this project. But the project itself, and it's a lot more than just these timber mushrooms. Yeah? It's about the square. It's about rejuvenation of an area of the city. It's about including an old fresh produce market. It's about a museum. It's about these urban sculptures. And it actually has a really long history, because the site, the plaza, the square, back in 1973, the year that I was actually born, another link to my adventure to this project. That's when the first event happened to actually make all of this possible. I'll show you that a little bit further down the line. Yeah. A quick introduction to the teams and the situation. The actual owner, of course, being a town square, is the city of Seville, but it's a concession. So there's a general contractor who owns the site for 40 years and was responsible for building it and for maintaining it and operating it. The interesting thing here is, it gave us two clients. So we had the city of Seville, who were always in the background and trying to influence it because they knew they'd get it back at some time. And also the general contractor, who was used to building concrete highways. And you can see that it's not a concrete highway. So, he knew he was going into something new. He wanted to do something different, but nonetheless, the engineers and the site manager and the guys that came onto the project, they were more used to building, knocking out concrete highways. So that was quite challenging. Sathir, but in the end, we worked very well together, and had a fun time delivering this too. The architect, Jürgen Meyer H., a small architecture practice based in Berlin. This was pretty much their first international project. So for them, for Jürgen, it was his baby. This was his big project, and so he had they focused. They had a team that was very focused on the project, and they paid a lot of attention to it. And then us over Arup Partners, Arup for short, as engineers, we did the structural and the mechanical engineering, and Finnforest Merck, they're called Metza Wood now, are the timber contractor, who also joined us relatively the beginning or in the middle of the design to help with the timber, and then erected it on site. So big mix of players, also geographically and culturally, we're all a bit different. The city of Seville, they're southern Spanish people, then the general contractor, big company, the architects from Germany, the timber contractor from Germany, us, English engineers, but based in Madrid. At some meetings, people spoke German with each other, and others English, and others Spanish, and sometimes it was even difficult to find that common denominator in the language during this adventure. But as you can see, on opening day, we were all standing together and hugging each other and enjoying a cerveza under the the timber mushrooms. So to start off, have a little, I'll show where it is in the urban sense of things. Then I'll go into the competition phase and the design that we came up with, the proposal that we came up with, and what we won the competition with. Then I'll explain a bit the design development. I'll go right into the connection design, always the interesting bit about timber structures. And then we'll look at the site, and we'll see how the whole thing evolved on site. So here we have in the middle in red is the Plaza de la Encarnación. That's our square, which now you can see sits pretty much in the middle of the town of Seville. You can see on the west-hand side is the river, on the east is the ring road. But up to about 2000, that wasn't the case. The main focus of activity, be it tourism, economic, stores, cultural, everything was happening just south of our square, down to those large green spaces, where the old palace is, the cathedral, and everything was happening down there. In the north bit, it was pretty much forgotten. And so the mayor, in the year 2000, wanted to use our square, which since the year 73 was pretty much derelict, said, okay, let's use the square to relink the northern part of the city and rejuvenate that area and use this urban regeneration to pull all that tourism and all that the shops and the restaurants and pull that northwards. And so now our square is indeed smack dab in the center of Seville, making it an important one. And so in 1973, there was a fresh marketplace, which they tore down for unknown reasons. I've been down, every time I went down to site, I would always try to ask some local, why did you actually tear down this marketplace in the first place? I never got an answer, but of course I'm happy because it allowed us to realize this project. So they tore down the fresh marketplace. They wanted to just build a shopping center, basically, about 20 years later. After thinking about it really hardly, what can we do with, what can we do with this site in the middle of the city? Oh, we'll build a shopping center. Not a great idea. Luckily, they started the excavation and found Roman ruins. And then immediately had to stop. Surprise, surprise. Actually, it shouldn't be a surprise because Seville is an old Roman colony. Anywhere you dig down into the ground, you're going to find these ruins. But yeah, that was like the second event that happened pre-project. So then they sat there, okay, what are we going to do with these Roman ruins? And that took a while, to think about, until the mayor back in 2000 said, okay, that's the square, we'll use it. We'll bring back the fresh produce market. We'll use the ruins to make a museum, and we'll rejuvenate the square and link the northern part back to the southern part. Really, very, very, very good idea. So that was the mayor's vision. The international design competition was organized, and we entered with as mentioned, Jürgen Meyer. And this was our competition winning scheme. Basically, in the south of Spain, in Seville, any kind of public space that you create, you need shading. Right? You need something. Between the months of June and September, it pretty much gets to 45, 50 degrees Celsius in the sun. And if there's no shading, then nobody will use it. So these parasols, kind of based on some of the existing trees that other squares have, some of the curvature from based on the cathedral vaults. That's kind of where these parasol shading devices came from. And the city of Seville said, great, that's what we want. Something completely different, which surprised us too. So now we're thinking, oh wow, we won. Now we got to build this. Okay, so we got down to work. This is another image. Wait a second, that's not timber, is it? No, I have to admit the original competition scheme that we came up with was a steel structure. Yeah. So before I show you then how in the next stage of design we moved over to our timber design, let's just have a look at what have we got in the Plaza de la Encarnación. Well, in the basement, 5 meters below ground level, the existing Roman ruins. Yep, so we have a museum for these ruins. Then at street level, within that glass facade, is the fresh produce market. So there's a nice large space for them. They were actually the entire time since 1973, when the market was knocked down. There in the top right-hand corner, there's a little shed that you can see. They were squeezed into that like a temporary market. So they were, once we started with work on this, they were always cheering for us. They really wanted this marketplace to come back. Above the market, we have a raised plaza level, which kind of creates a space for public events, be it political events, sporting events, cultural events, concerts, and so on. And as mentioned, here already shown in timber, shading the entire square are the parasols. Additionally, inside up top, we've got a restaurant, a cafe, which is integrated into it, and there's also a walkway, which meanders over on top of the structure, which offers views of the city and the surrounding cityscape. So the uses are all organized horizontally at each level, and at the same time the stems from our mushrooms, from the parasols, they provide vertical connection visually and also through escape stairways from top level from the walkway. You can see at the far end there's escape emergency stairways, and the two parasols in the middle, they actually house a concrete core for elevators and stairs and services for up to the restaurant at high level. I'll also show the rest of the structure before we head on to the parasols, because it's got a bit of everything. It's not only the timber mushrooms, but there's concrete, there's steel, there's every material that we needed. We used it. The foundations, obviously, concrete foundations, piled foundations, because not only the ruins, but there's 5 more meters of just sand and bad soil. And also because we have a lot of loads coming together in specific places, because we're working around the ruins. The Roman ruins, they pretty much stayed in their place, they stayed put. And we had to coordinate with the archaeologists, okay, where's an area where you didn't find anything, no excavation happened, or where's an area where they're not really that interesting and you might want to put them in a catalog. And then they gave us 6 spots. Oh, okay, and those were the 6 spots for all of the structure to be founded on. So that was quite tight. And we'll see later on how that influenced the design. The museum and the marketplace are a steel structure, large Virendale trusses spanning in one direction onto these discrete pile foundations, and then a steel concrete composite deck. You can see the purple beams forming the floors for the museum and the raised platform above it. And as mentioned, the cores that support the restaurant at high level, they're made out of concrete, just to house the elevators. And the structure for the cafe restaurant at high level is also a steel concrete structure, mainly for fire reasons, and for the higher loads from the cafe. And now let's look at the parasols. Yep. Here we pretty much see the design, our first ideas. We thought we've got parasols, we've got kind of trees, we can make they're cantilevering up, so we have these stiff vertical elements. From these trunks, we can kind of cantilever out and connect it all, and then a space frame pretty much appeared. And when you think space frame, the first thing you think of is steel structure. But then later on, we would have to cover that with a facade, with a skin, and then we've got a separation of structure and skin, which is more material. We've got a lot of cantilevers. As engineers, cantilevers aren't really that efficient, so they're a bit pesky. Try to get rid of those. The architect didn't like the separation. So we moved on and started looking at some shell structures, something where the structure and the facade, one and the same constructive element. That really wasn't stiff enough, so maybe doubly skinned to give us more bending stiffness. That started leading more into volumes that we're actually defining, and then you kind of shave away from you could imagine this big cube. The entire parasol structure is about 120 by 80 and 30 meters high, and then you just shave away from the sides to give you that that geometric definition. So we're much more looking at some kind of global element which defines our 6 parasols and not 6 individual parasols. You know, this is one of the first sketches. Up top, you can see that old idea of the stiff cores cantilevering and then just cantilevering out from those. And at the bottom, a more homogeneous, one big structure defining the entire thing with grids or, you know, some kind of axes maybe or ribs. And I don't know, when I was young, I played with these. I think everybody probably here. We had these little dinosaur balsa wood flat packs. Well, they probably weren't called flat packs yet, but yeah. And you kind of take them out, and then you have these ribs, and you kind of put them together in an intercombing fashion, and that defines the volume, the geometry, and at the same time has your structural elements. So why not do the same thing with the parasols? Well, everybody loved it. The architect immediately put together a first render from the geometry model. We sat down. We were sitting down with the timber contractor, and he made a scale model of 1 to 50, and yeah, it fit and it works. Manufacturing, fabrication-wise, also, you know, no doubly curvature problems. It's all just flat elements with curvature in one direction. You cut them out with like a cookie cutter, you know, and within weeks we had all the axes defined and all these elements. We got in there and did a bit of optimizing of the geometry, tweaked the geometry a little bit. You know, we still had some cantilevers. You know, some of those ribs are still cantilevering out 2 directions, so put a bit more material where we need it. Introduce a bit more curvature, you know, to get more arching action, and so that it works more in compression and less in bending. And with all those workshops with the architect and with the timber contractor, we changed our design to look like this. Yeah, so that was at the end of concept, about 2004, just the time when the concessionaire was coming onto the project. He was probably surprised, because he thought, didn't I sign up for a steel structure? Now I've got a timber. And the guys in Seville were also like, timber? You know, they've never built something out of timber in their life. North of Spain, you get some timber construction. South of Spain, concrete, maybe a bit of steel. And they're like, you know, they've never seen something that scale, that size. But I'll show you why, some of the reasons why we changed to timber, and it convinced them. Yeah, it definitely convinced the city of Seville, so that they gave us the green light to go ahead. And also keep this image in mind, or we can compare this image with what we saw at the very beginning. And I think we, you know, as a design team and the contractor in building this, we managed to, this was 2005, and opening day was 2011, and I think we really stuck to the original image of what we wanted it to look like. At this point, we also did some shading studies to actually get a feel and get an idea for how much, because here we defined a distance between these ribs of 1.5 meters, which had more to do with if some of the elements are just hanging between 2 intersections, you know, what would be an efficient span for them to span as, but also to see a bit how the shading on the square actually works. You can see on the bottom right a bit. So why timber? The guys from the city of Seville asked us. Well, first of all, it's not just any old timber. It's an engineered timber product. Most of you probably know laminated veneer lumber. In this case, the product is called Curto Q. So the veneers are all about 2 to 3 millimeters thick, glued together, and every 3rd to 5th veneer is then rotated by 90 degrees, and that gives us nice big plate elements. Because as you can see, we didn't have just the structural elements weren't just beams, but also in the trunks, you know, we had these big plate elements. And that's the first reason why timber works a lot better. Steel, with these dimensions, would start to buckle. You immediately start getting buckling problems. With timbers, with the Curto Q, we wouldn't have this problem. Another factor, well, back to these Roman ruins and the foundations. You can see within the retaining wall, the excavated site, we had 4 spots where we could only found the structure. Additionally, as soon as we won the competition phase, they had been very patient with the site for 30 years, and then we won the competition, and they immediately wanted us to start building something. Okay, start moving, get moving. We're like, oh, wait a second, we have to design it first. Well, can't you? Well, the excavations happened, so why can't we build the foundations? Okay, so we kind of did a pre-design, and the foundations were built immediately within 6 months. They were, oh, okay, great. Now can we build the parasols? We're like, we haven't. It was that kind of rhythm and what they were asking for. So we had these existing foundations. These parasols, they're mainly they're sculpture almost. So they're carrying their self-weight, and timber has, the strength to self-weight ratio is a lot better than steel or concrete. Not even going to talk about that. So we actually, timber would be the most lightweight structure that would actually be that can fit on these built foundations. And we also used it because the architects, based on experience on a previous project, they had a roof construction, and they were looking for a way to get the roof watertight. And what we basically did with this timber, it's not exterior timber, it's not external, it's actually internal because it's protected by a coat of polyurethane. So around every single Curto element is protected, not hermetically, it's not completely sealed, but it's protected from the elements with a 2 to 3 millimeter layer of polyurethane. And then on top of that is a final coating of UV protected painting, which gives the final finish color. Yep. So this actually allows us to be able to use this timber as a structure element because it's not external. This is a slide comparison based on the Eurocode. If it were external, we'd be working with a class 3, and the strength reduction factor would be a lot higher. Reduced by 30%. But if it's internal, you just reduce the strength by 10%. And the same with deflections. We can control deflections a lot better, especially over long term. So that actually, from an engineering point of view, allowed us to use this as a material. And the polyurethane also comes into play when we're talking about maintaining the structure. The steel structure, we'd have to paint every so often. The polyurethane, life expectancy of, well, actually infinitely, but the producer gave us 50 years just because there's no other built example. But nonetheless, maintenance-wise, the timber with the polyurethane is still cheaper for the concessionaire than the steel structure. So that pretty much got everybody convinced. The city of Seville, they were happy to have some timber mushrooms in their city. They'd never heard of that. But that kind of fit into the concept of, well, up north, that city of Bilbao, they've got a nice museum from, they got a nice Guggenheim from Geary, so, we'll do something that puts us on the map too. The concessionaire, they were happy because new material, but, maintenance-wise and cost-wise, it all fit into their criteria. So we got down and started designing the connections. Yep, as I mentioned before, we basically have that grillage, that timber grillage, and there's every 1.5 times 1.5 meters, we have an intersection. That gives us about 6,000 intersection nodes, where we had to define, how do they actually meet up. The general principle is that one of the timber elements is always continuous, and the other one, too, gets connected together. Yeah? They're all stiff connections, they're all moment rigid connections. But instead of transferring a moment, we split it up into two forces. So we have a push and a pull at top and bottom level. And at the top, so we just have steel bars. You can see the far left is the general principle of this connection with the steel bars at top and bottom, taking up the push-pull forces, and the one element being continuous. Yep. This didn't really give us enough, it could transfer the high forces, but it didn't give us enough stiffness. The connection was a bit wobbly, basically, in it. And so what we decided is to post-tension the rods. Once those rods are in there at the top and bottom, why don't we stiffen it up nicely, get a nice stiff connection. That worked, but then it started getting really heavy because we're more steel elements, more steel plates, they had to be a bit thicker, and we had that limitation of the foundation that had already been built, so we couldn't just make the connection detail too heavy. So we were faced with that problem of trying to find a solution for something that had to transfer high forces, but had to be lightweight at the same time. And so with the timber contractor, we continued working and setting up mock-ups at 1-to-1 scale, and trying to, on the far right, you can see how we're trying to take timber out where it wasn't necessary, or actually inserting wooden plates instead of steel plates. And the weight went down, but then the capacity also went down. And this actually took, this took quite a while. But not only because it was technically difficult, but because at the same time, there was a bit of political upheaval in the city of Seville. And there were some people on the city council who started having doubts, and then the concessionaire, he wanted more funding from elsewhere. He didn't want to put all the money in himself, so he was looking for a bank to support him. And all this came, at the same time. When then they'd ask us, well, how are you coming along? We're like, oh yeah, well, it's difficult, but we're getting there. We're getting there. Like, well, don't put too much effort into it because you might not build it. Well, okay, well, so how do you kind of try to design a connection, which is really difficult, and at the same time try to do it low key? It was a difficult time. Luckily, the contractor, the concessionaire, said, well, hell with it. I'm just going to start building, because all the concrete and all the steel for the marketplace and the cores, well, that was all finished designing. So he just went ahead and started building that. And so, there was stuff happening on site, and then that kept everybody happy again, and it kind of, went better for a while. And we could also move ahead with our connection design, and then we finally came up with a solution of sticking with the steel rods, but actually embedding them and gluing them with an epoxy into the timber. Yeah, you can see in the top left how these bars are poking out. The rest of the solution is the same. Those bars stick out, and then we just attach metal plates. And there's always two plates that meet each other, and that big bolt that you can see, that's the one bolt that they have to connect on it, that they actually have to put in place on site. So that now we've got a connection with these steel threaded rods, basically. They're glued in with an epoxy. And then the forces get along that length of 660 millimeters between the steel rod and the epoxy get transferred into the timber. So we can transfer our high forces, lightweight solution, and on site it's pretty easily they can just put it together with one bolt. And the timing was perfect, because it was just before Christmas. The city council had started getting involved, and we're wondering, where's the timber? Why are there no timber mushrooms growing on the site? And so they drummed together an important meeting on December 23rd, I think it was just before Christmas. And the architect and I, we went up and presented. We're like, actually, good timing, because we have the solution, and we can go ahead with this. But we also had to explain to them that it wasn't a mechanical connection anymore, which is the big difference, because now we're using glues. Hasn't been done very often. It's actually a chemical connection. And you could start seeing some of the guys in the city council scratch their heads and, I don't know if I like this. But luckily, one of the older guys there, he was sitting on his chair, and he kind of looked up and he was scratching his head. Well, 20 years ago, I sat on a chair and it was all nuts and bolts, and he looked down. Now I'm sitting on a chair, it's all plastic and glued together. It'll work. I'm okay. We're like, that was all it would have taken to convince him? Yeah. But nonetheless, we had sold him with a technical presentation and with the practical side of it. But and then immediately, they said, okay, well, next week start building on site. Well, no, wait a second. We've got the connection detail. Now we got to figure out, this is something new. There's nothing like this around on the market. First, we got to figure out, what does it do? First of all, we want to know the capacity. What are the actual forces that we can transfer? So we started doing some testing with the help of some universities in Germany. And on the left, you can see the result of the first test. Unfortunately, it failed, which is not what we wanted. But of course, we didn't want it to fail, but we didn't want the timber to fail, because the timber would have been a brittle failure. So we reduced the steel grade, tested it again. And on the right, you can see that now the failure happens in the ductile steel. Yeah? So it's a more controlled actual failure. So with that way, before, there's also all those steel plates. A lot of, we're transferring compression forces, so you got to check those to make sure they don't buckle. Had a factor of safety of 2. I think in all of this, how these elements were put together, these were then separated, tested separately in another lab, and then all the elements were put together and tested again in their final assembly. But those gave us the actual capacity of the connections, but we also had to do some thermal testing because, as I mentioned before, it gets hot in Seville. And so now we've got these steel plates, basically, so that means the sun is constantly shining on the steel plates. And anyway, if you walk across the sand on the beach on a hot summer's day, then the surface temperature of the sand is even hotter. Same thing with the steel plates. They'll really heat up. And then while they're connected to those steel rods, the steel rods will heat up, and they're glued in. So that's kind of dangerous. We did some tests. Hold on, I got a little video of the simulations that we did, and heat up the outside plates, and yep, just like we feared, the rod also so heats up. So we sat down with some timber. Get back to with some glue experts. There's experts for everything nowadays. How can we solve this? And we came up with a post-curing process, which basically means taking the timber element with the steel rods glued in and putting it into a kiln and treating it with heat. Turn up that kiln to about 55, 60 degrees Celsius, leave it in there, and then we're basically changing the glass transition temperature of the epoxy. So if you heat the epoxy up on a molecular level, it actually remembers that higher temperature. And then later on, when it's sitting in Seville, then it can resist a temperature of up to 80 degrees. And we had calculated that it would go up to 70, and then with a couple of factors of safety, we ensured that this epoxy can actually then resist up to 80 degrees in the blaring sun of Seville. And with all that, we pretty much had a connection detail, connection design, which worked. I mentioned we had 6,000 of these intersections, so we didn't want a different connection type at each node. So we started setting up a catalog, a little kit of parts. And we started basically with all the different timber widths that we had, which were based on fabrication from the timber contractor. So the smallest timber element could be 68 millimeters wide, and the largest was 221 millimeters wide. And so there's a different connection for each of these timber widths. So the smallest one just has 2 rods, which are glued in, and at the bottom you can see the big one has 4 by 3, I think 12 rods glued into the timber. And that kind of gave us you can work with just having 6 different connection types. And with that, we could, having the connection defined and having the material defined long ago, we could finally actually buckle down and do the structural calculation of the structure. That, as with many projects, starts with the geometry. These are the geometry models. Jürgen set it up in Rhino. Most of you are probably familiar with that. Defined the geometry, and I have to really give it to Jürgen. In the entire 5 years of the project, the geometry didn't change once. Show of hands, who's worked on a project for longer than 5 years that didn't go through 273 geometry in steps? So that was one solid, no iterations on the geometry. We took that, plugged it into our in-house software, GSA, and set up our big structural model. I actually have to say it's a good thing that the design of the connections took about 2 years, because 2 years ago we wouldn't have had the computing power to actually calculate the size of the model that we ended up having. So you can see in blue the trunks, those are the shell elements, and up top in green is the area of the canopy, as we call it, and those are all beams. That's that grillage of beams with rigid connections. But seeing as we don't have a typical roof as in other structures, we're missing that diaphragm. We need that. We're missing that horizontal stiffness. So I started introducing some diagonals, just diagonal bracing in those 1 by 1.5 times 1.5 squares. And mainly we placed them underneath the walkways so that you wouldn't really, so that visually you wouldn't see them. But of course, once we started introducing, once engineers in the team started introducing diagonals and stiffening it up, and it works a lot better, and oh yeah, if we put something there, we would have loved to put diagonals everywhere. But we, just under the walkways. But another area, once again, these pesky cantilevers. We were trying to control the deflections of the cantilevers. And so also around in the canopy, in a ring fashion, we also introduced some more of these braces. And they kind of work when you got a vase and the flowers are wilting, and you just put a string, you tie the string around it, you can control those deflections. So the same thing is what we were trying to do with some of the extra bracing in the timber structure. So we finally had our structure, huge, huge model. We got it to run. Well, we defined all the timber with a thickness of 68 millimeters because we thought we got to save weight. So let's use the thinnest timber we have. Did a calculation, and you can see the forces. Here we have the axial forces. These are the moments. I think this is where I can launch a model of the deflections and see how it also kind of, hold on. Do I see something? Nothing happening there. Okay. Okay, we will skip that one for now, though. Yeah, there's something different on this screen than on that screen, that's why. Space? No? Doesn't work. Okay, we'll just move on for now. There we go. Those are the moments. But it's not just as simple as doing one calculation and saying, oh, all of our, because we had that, all of the structure works. If you remember, we had a collection, we have a kit of parts, we have a catalog of different connection types. We had to find the structure with 68 mil wide timber, so it had those tiny little, the lightweight connection, but also the connection with the lowest capacity. And then we did one check, basically, and we noticed, oh, wait, well, here we need a bit more timber. Here we need a higher, we need more capacity in our connection. So we have to upgrade certain elements. Of course, if we upgrade those elements, they also weigh more. So that means we're introducing more self-weight, which is what the original calculation was based on. That's different now, so that we have to calculate it again. So we're into this iterative calculation. We thought we're not going to do this manually. This will take way too long. So we set up a little spreadsheet which read the values from our calculation, extracted them, did that check. Okay, at that node we have 50 kilonewtons. The connection detail has a capacity of 40. Okay, we need to upgrade. That increases the weight. Let's run it again. And so we had a couple of big computers working for about a month, doing 43 iterations until the entire structure converged. And we finally had a structure which was in complete equilibrium. A couple of other factors which influence this calculation. The geometry of each of these ribs is quite different. I mentioned the cookie cutter, and working with the timber contractor, we tried to limit the angle between the axis of our actually physical element and the grain, because once you get higher than 7 degrees, the strength goes down pretty quickly. So that the angle of each of the elements was also in our calculation, so that actually that little kit of parts of just 6 connections then kind of expanded and became a big matrix of 12 different connection types, different angles, and then that gave us actually the capacity of the connection detail. But yeah, the spreadsheet did all on the right hand side in green. You can see it awaiting the forces from the model. Did all those checks, It also enabled us to actually issue the information to the timber contractor in just 12 Excel spreadsheets. We didn't produce a single drawing. We didn't need to. The geometry was defined in the Rhino model. All the forces and which connection type and which timber thickness were defined in our spreadsheet. Okay, mind you, this was a huge spreadsheet. I think this laptop probably couldn't open the Excel file. There was so much information in there. But nonetheless, 12 files was all that we needed to send the data over to the timber contractor, who then could use that to start cutting out the timber elements. And also he then went on to do the calculation of actually the bolt length and the bolt diameters and all that, the detailed calculations. But mainly he could start fabricating, because obviously doing these iterations and explaining that to our client wasn't so easy, because he had expected us, okay, we finally got that connection detail solved. They were waiting for timber to arrive on site. So once this robot started fabricating, he worked 365 days non-stop to cut out all the pieces for our parasols. Their factory is based in Munich. And here you have a look of what's going on inside, where the timber elements are cut out, and they start adding on some of the steel elements to do as much as possible in the factory. Especially important was gluing in the rods with the epoxy. We want to do that in a controlled environment. Even though that was very detailed and very a lot of quality assurance, and they really followed it step by step. But interestingly enough, the way they figure out if there's enough glue, in that hole for the rod is there's two holes, one where they pump the glue in, and at the very end there's another one. Once the glue comes out, then okay, there's enough epoxy in the hole. This is not a very sexy image, but it's the kiln for the post-curing process. So a very important part of the fabrication, because the timber elements get moved into there, heated up so that they can resist the heat down in Seville. And here we can see some of the guys handling one of these really big. Now we start to get a sense of scale of how big some of these timber elements actually are. And the Germans that work in this factory, they're big guys, so that that element is even bigger. You can see in the middle those openings. That's where other elements perpendicularly will be connected. And you can also see that it's still just the laminated veneer lumber, no protection yet. They were then sent down to Seville, where they started applying the polyurethane. Here we can see a big warehouse just down the block from site with all the elements in front. They're protected with the polyurethane, and in the back awaiting application. Most of it, pretty much 98% of the surface was a surface application, but you can see some of those strips which are still, there's no polyurethane. That's where later on, on site up in the air, they actually still have extra metal elements that they have to, like shear angles and stuff that they have to fit. And then later on, they just went through and painted it on, the polyurethane. And here you can see the elements, also in a myriad of geometric shapes and sizes, lying on site and awaiting their erection. Here also, once again, you can see a car in the background, giving us a bit of scale for the elements, how big they actually are. And with that, we can start looking at the site. But let's go back to our year 1973. This is the old marketplace. It doesn't look bad, which they tore down, as mentioned, for no reason, but we're happy that it actually happened. This is what they used the site for 20 years, a beautiful parking lot, with not much happening in the way of a public plaza. So even in the year 2000, when they wanted to build the little shopping center, they started excavation. They found the ruins. They pretty much also just left the ruins lying there on site. Even less of a public plaza. Now, now just nothing happening. And then finally, construction activity started. This was the phase where, the city council was kind of, I don't know if we've got money for this, and we're like, ooh, this connection design is really difficult, and the contractor was like, well, I'll just build something out of concrete. And those are the concrete cores that went up. During this phase, the locals called it the lighthouses of they weren't called the setas. They weren't the mushrooms yet. That was still the lighthouses, los faros. You can also see the site. It's a tight fit, and the city of Seville didn't make it very easy on the contractor either. So the bottom and the middle, you can see the bus stop had to remain in use for the entire time. It was actually a bus interchange. All the buses from the north came down and just kept on clogging up the site. Cross-square traffic had to also be maintained in a U around the site. Going back, the delivery vans had to continuously have access. It was horrible. So for that reason, that was pretty much the state of the site previously too. There was nothing, there were no stores, there were no restaurants, there was nothing in those buildings that you can see, defining the square. There was nothing really. There was one cafe in the way, way, way back, which only survived because of the people that actually had work on the site. Otherwise, it was pretty dead. Here you can see the steel structure going up for the museum and the marketplace, and also on top of the concrete cores for the restaurant. In the bottom left, you can already see one of the concrete plinths, where one of the timber trunks then supported on. And then while we were busy doing 43 structural calculation iterations, the timber trunks were built. They started getting antsy again, and they needed something to build on site. So the 4 timber trunks started going up. Here you can actually see some of the biggest elements. They're about 2.5 by 16 meters, 2.5 meters wide, 16 meters long. Some pretty big fellas. And here you can see one of the trunks ready, finished. Here we can also see a bit of the fire strategy, which is basically, you can see that skirt, which kind of is around the base of the trunk, which gives it's just direct physical protection. It's sprayed concrete, so that no fire, a trash can or any fire that happens on the square, could present a danger to the timber. And otherwise, the canopy itself actually has a fire rating of 0, because there's enough time for all the people on the square to actually excavate and get off of site. So this is the main fire protection that we have for the timber structure. And finally, in 2010, it was summer of 2010, construction of the canopy started, starting on top of the built trunks, these big elements. Once again, those big German guys taking one of those elements into their hands, and you can see how big that element actually is. It was quite scary watching that happen. And so from the trunks working outwards, the canopy grew, which would have once again given us cantilevering structure, which we didn't want. The timber contractor also needed a surface, to work from, some kind of base. So we have this temporary scaffolding below the structure, and which kind of forms the working platform for the timber contractor, and gave us the possibility of putting temporary supports every 3 intersections to ensure that the timber structure, structurally would work in its final stage as conceived, and in any kind of temporary construction phase, it always had these temporary supports. Here's a nice little picture of basically showing our catalog, the kit of parts that we had previously a year ago defined, and that's what reflected by the different elements on site. On the left, you got really small plates, and on the right, you've got some big plates, which weigh about 10 to 15 kilos each. Here a bit of an up-close shot of some of the other connectors that we had. The top left are shear angles. Shear forces were just transferred with normal shear angles, which were nailed in. Top right, we have the bigger steel plates where the steel bracing, the diagonals are connected. And on the bottom, once again, those little steel plates for our connection. And so the timber, the parasols started going up, obviously with a lot of this temporary scaffolding, to give temporary propping and form the platform. Everybody in Seville was very, oh yeah, now we really see something growing. This is unbelievable. Timber mushrooms, never seen them in our lives. Can't wait till this is finished. And then I think, this is a month before opening day, and then all of a sudden the press just started giving us really bad press, and it's way too big. They got the scale wrong. The volume of the structure is wrong. It doesn't work in the square. And okay, admittedly, with all this temporary scaffolding, it looks a bit bigger, but they just gave us a hard time. It was unbelievable, and so with the guys from the scaffolding, in 2 weeks, took it all down, and were able to present it one day before opening day, like this. And then we got good press again. Well, luckily. No, and then we all were quite relieved, actually. The city of Seville, the architect, the concessionaire, us as engineers, quite happy to finally be able to join in the opening celebrations of after 6 years of this adventure. So just to finish off, just wanted to show some images from different points of view, from on top, from down below. This is up on top of the timber. You can see on the right the opening where the cafe, the restaurant, is tucked in there, and the walkways kind of come out of that area. And in the background, you can see the cathedral, Seville, where supposedly Columbus's remains are buried. Here, another image of the walkway. Walkway is just a simple steel structure, basically just transverse ribs every 1 to 2 meters, and then steel plate and really high balustrade for security reasons. Actually, the walkway was also supposed to go all the way to that really far parasol at the very end, but that would have meant crossing over that one cross street that we saw in the construction photos. And somebody in the city council wanted to make wanted to leave his his opinion on the project. Said, oh no, that's dangerous. We can't have a walkway over a street because they might throw things down onto the cars. Like, why is that any more dangerous than throwing things onto people on the square? But we had to cut the walkway short, but didn't really change it. It's still a really nice. Here's inside the cafe looking out. I really like the fact that detail, that connection detail that we worked on for so long, you can actually see it. Everywhere you can always see that there's something special there holding it together. Here's another image, because the parasol, the canopy structure pretty much splits and goes below the cafe and above the cafe. So that facade is looking inside the cafe, and you can see how the timber splits up. And here, another shot on a typical summer's day. You can see the pattern at ground level in the shade, actually. And you can kind of tell how pretty much all of those Spaniards, they're all in the shade, right? Everybody is in the shade. The only guy on the left who's in the sun, that's actually me. Even after 6 years, I still didn't get it. I still wander out into the sun and whoop, back into the shade. The fresh produce market, when these guys moved back into their new market, they were crying for joy, actually, because they were stuck into a little temporary market for 30 odd years, and they finally had they could set up their stalls, and where all the local people could finally go back to just a square and buy their vegetables and fruit and vegetables for the weekend. This is Occupy Metropol Parasol. They also came out in big numbers and set up base below the timber mushrooms, which we actually thought it was quite good because that way it was the first real test of how many people could, it was like a load test of the steel concrete composite structure and the stairs, and when they started jumping, and it worked fine. It was great. For the Euro Cup last year, they also had set up big screens and had public viewings where all the guys in red were cheering for their team. That was quite good. The museum, much overlooked, but actually a really nice space. All those Roman ruins. The columns that are in vertical position were found in a vertical position, and they're like the columns of courtyards of these rich Roman people. Some really nice mosaics in those courtyards. Some really nice finds down in the museum. And to finish off, just one of my favorite views, which is one of many. Whenever you're below the structure, there's always a different geometry and a different flow and a different light to the structure. And with that, that ends my adventure in engineering. Thank you very much.